Okay, there we go. All right, so we're going to take a look at curvature a little bit more in this section. This is the third part of section 13.3, where we're going to look at curvature for plane curves. We're looking at a two-dimensional function y equals f of x. We've already looked at how to look at three-dimensional space curves when we're given a parameter t. We're going to take a look right now at how to find the curvature of a plane curve. And then we're also going to talk about what's called the normal and binormal vectors. So get my pen, make sure this works. Let's draw classic smiley face. We'll make it a vector. There we go. All right, so what if we want to find the curvature of a plane curve y equals f of x? We saw yesterday that we get this curvature function kappa of t if we're dealing with parametrics, which can be defined in one of two ways. We saw that it was the magnitude of the derivative of the unit tangent vector divided by the magnitude of the tangent vector. Sometimes, especially with our last example yesterday, we saw that that's fairly difficult to compute in practice. And so a more handy version only deals with the position function r of t or its derivatives. So we saw this version also. Magnitude of r prime t cross r double prime t divided by the magnitude of r prime t cubed just prevents you from having to calculate the unit tangent vector and take its derivative. So in the specific case we're interested in now, if we want to look at something in a two-dimensional sense, we're going to let our x component be x. And my y component, if my curve is y equals f of x, that means I can define my j component of my vector as just f of x. That's my y value. Okay. And I want to figure out kind of a shorthand for what the curvature would turn into in this specific situation when we're dealing with a plane curve in two-dimensional space. So let's use, this was the more convenient formula we saw yesterday, so let's derive this. My r prime in this case would be equal to 1 and f prime x if I take the derivatives of r of x, sorry. R double prime, we're going to need. R double prime would be 0, f double prime x. And so then computing, I'm going to do this in a couple different steps. I think first thing I want to compute probably is the numerator. So let's do r prime cross r double prime. This is going to be my 3x3 determinant for my cross product. I'm going to get 1 f prime x. Because we're dealing with a plane curve, which means we're dealing with r2, my k component would be 0 since I don't have any z coordinates. My r double prime would be 0, f double prime x, and again, my z component would be 0 since I'm dealing with a plane curve. Taking my cross product, I would get I times 0 minus 0 is gone, minus j times, let's see, we're going to get 1 times 0 is 0, minus 0 times 0 is 0, plus k times, cross off first row, third column, f double prime minus 0. And so actually all I'm left with in this case would be f double prime x times the k vector. So 0, 0, f double prime x. And so our numerator, we need the magnitude of that. So the magnitude of r prime cross r double prime would just be the square root of f double prime of x squared, using my vector norm formula. When you take the square root of a quantity squared, we get the absolute value of f double prime of x. Just in case it's negative, we're going to want this curvature to be positive, so we don't want to consider negative values of f double prime. So that becomes my numerator up here is f double prime x absolute value. The denominator, we actually already have r prime calculated. So to get the curvature, let me scroll down here. This was, let's do that calculation off to the side here. There's r prime, so let me do this in blue. My magnitude of r prime x, we're going to need to cube it, but let's calculate it first, would be the square root of 1 plus 1 squared, so 1 plus f prime of x squared. And that's going to be my denominator, and then I'm going to have to cube it because of the power of 3. So putting it all together, we get f double prime x absolute value over the square root of 1 plus f prime of x squared. All of that is going to be cubed because of our power of 3. And so a more compact way of writing that is the absolute value of f double prime x. And this is kind of the punchline. You don't have to rederive this every time. You can use this result now, but I just wanted to show you where it comes from. Over 1 plus f prime x squared. The square root we know is a 1/2 power. When I raise the 1/2 power and I cube it, this is going to turn into a power now of 3/2. So this right here, I'm going to highlight this. This is how I calculate the curvature of a plane curve without having to rederive it every time. This is a good formula to know. So we wouldn't use this for parametric functions that are in 3 space, but for 2 space, anytime y is a function of x, this would be useful. So how can you use it? So let's take a look. Let's say we wanted to find the curvature of our parent function parabola y equals x squared at the points 0, 0, 1, 1, and 2, 4. Well, if I need curvature, I should probably compute my curvature function. So kappa of x, y prime, y double prime, absolute value over 1 plus y prime squared to the power of 3/2. If y is x squared, that means y prime would be 2x, which means y double prime would just be 2. So I get the absolute value of 2, which is 2, over 1 plus 2x quantity squared would be 4x squared to the power of 3/2. And so all I'm going to do is I'm going to plug in my values of x. X equals 0 at the vertex, x equals 1, and x equals 2, and see what happens to the curvature. So if I do k of 0 or kappa of 0, I'm going to get 2 over 1. So I'm going to get 2. If I do kappa of 1, I'm going to plug 1 in. I get 2 over 5 to the 3/2. You put that into your calculator, that's about 0.18. And if you do kappa of 2, you get 2 over, let's see, we put 2 into this. 2 squared is 4 times 4 is 16, so 17 to the power of 3/2. Getting even smaller. So the interesting thing to note here is that as x increases, the curvature is getting significantly smaller, which would mean we would expect the graph to get more linear. Since we saw yesterday the curvature of a straight line should be 0. It looks like this curvature is approaching 0. If you take a look at the graph, in red, I've graphed the curvature function. So that's almost like this little bell-shaped, almost like a normal distribution, little bell graph. The original parabola in blue is y equals x squared. So looking at some of the pieces that we just found visually, I'm going to do them in green. At the vertex 0, 0, my curvature on the red graph is up at 2. So this would be the value of kappa equals 2 at the origin. That was this one. As we move out to 1, looks like our graph starts to look a little bit more linear, and our kappa value there is about 0.18. And if I was to move out even further towards 2, it'd be about here. Looks like my curvature is now only about 0.03. So the interesting thing to notice is that as you approach positive or negative infinity, as x moves very far off to the left, and as x moves very far off to the right, your curvature is approaching 0, which makes sense. It's nearly straight. As x approaches plus or minus infinity. Okay. And you might be asked on a WebAssign to figure out what the maximum curvature is. That would amount to doing your favorite technique from Calc 1, which is to take the derivative of the function, make a sign chart, and figure out what the local maxes and local mins would be. And really, curvature is probably the closest you would get to analyzing the behavior of the maxes and mins of the second derivative, right? You don't do a lot of analysis of the third derivative in Calc 1 or Calc 2. This is probably the closest you would get to analyzing some type of third derivative, because we are taking a derivative, or we would need to take a derivative of some portion of this function that involves y double prime. You're it's almost a slight measure of how fast the concavity is changing. Let that kind of sink into your mind for a minute. let's talk about the normal and binormal vectors, because these are really what help create space curves. So at any given point, we're kind of going to go back now to talking about free space and parameterizations. At any given point on a smooth space curve R of t, there are many vectors that are orthogonal to the unit tangent vector. We talked about that one yesterday. We saw that the unit tangent vector was equal to, and it was r prime of t, but we want to make it a unit vector divided by the magnitude r prime of t. So just to remind you what that was. We had a property in section 13.2 that says that if our vector has constant magnitude, it will always be orthogonal to its derivative. So in this case, because we know that the magnitude of the unit tangent vector is 1, this is because it's a unit vector. What that tells me from my postulate or my theorem, I'm just going to put 13.2 theorem. You can go back to take a look at the notes if you need the specific postulate that we did. But we know that that means that t prime dotted with t is going to have to equal 0. So in other words, t prime, let me make that a little bit more clear. T prime of t is going to be orthogonal to t. Okay, so what we're kind of starting to get interested in is, we know a vector that's tangent to the space curve, that's t. What would be a vector that's orthogonal to the space curve, or would form a right angle with this unit tangent vector? And so we're seeing t prime would work. The problem is t prime itself is not always going to be a unit vector. You might be able to find cases where it is, but we're very interested in measuring with unit vectors so that we're not over quantifying the magnitude of certain vectors. So just like we had a way to take the tangent vector and make it a unit tangent vector, we have a way to take this t prime orthogonal vector and make it a unit vector. We call it n of t, and we call it the principal unit normal vector. Sometimes you'll just hear it called the unit normal. That's what I'm going to refer to it as. The notation we use is n of t. All we do is we take the derivative of the unit tangent vector, which we know is orthogonal to t, and to make it a unit vector, as usual, we would divide by the magnitude of that vector. Okay. A couple things about this. N is orthogonal to t always. You will always form a right angle with your tangent vector and your unit normal vector. Also, this goes without saying here, but because of the fact that this is a unit vector, the magnitude of n of t is always going to equal 1, regardless of what t value that you're looking at. So it has constant magnitude, very similar to how capital T of t had constant magnitude of 1. A couple other points. Remember that t of t, capital T of t, the unit tangent vector, points in the direction of increasing parameter. We noted yesterday that the unit tangent vector, t, this gives the direction of the curve itself. Tells you kind of how the curve is positioned and which way it's moving. What n of t does, it doesn't really tell you the direction of the curve, but it tells you the direction in which the curve is turning. So if you wanted to kind of place an arrow in the direction of motion in terms of where things are turning, that is what n of t would give you. So n of t gives you the direction in which the curve is turning at each point, whereas t of t gives you the direction of the curve itself, since it's pointing in the direction of increasing parameter. Another thing, n of t is always going to point inward toward the concave part of the curve. So if your curve is concave up at a certain part, your n of t vector is always going to point in the direction of the concavity. If it's concave down, it's going to point in the direction of that concavity. Here's a real basic diagram, just so you can see what's going on. Here we have a point on the curve. I'm going to put that dot in blue. The blue vector that you see points in the direction of the curve itself, tells me that the curve is moving this way to the right. The normal vector tells me the direction in which that curve is turning. So in green, if you see my green arrow here, that would be my unit normal vector. And we can see that it forms a right angle and it's orthogonal to t of t. And since this is concave up, we can see that it's pointing in the direction of the concave up portion of that graph. Okay. So we've got a normal vector, we've got a unit tangent vector. Another vector we're going to be interested in is, what about a vector that's orthogonal to both of those? One that's almost coming out of this plane curves page. Considering this is a 2D curve, we could do this with 3D curves also. That's what we call the binormal vector. The binormal vector, we denote B of t. This is a vector that's perpendicular, or we could also say orthogonal, to both the unit tangent vector and the unit normal vector. And the way we define it, it is always going to be defined as the unit tangent crossed with the unit normal. Cross product because we want it to be orthogonal to both of them. You can't switch the order because we know the cross product is not commutative. So I would say the easiest way to remember which one comes first, we learned about the unit tangent first. Later, we learned about the unit normal. So the order you cross them is the order that we learned them in. We learned about t first. We learned about n second. That calculation will give you the binormal vector, which is going to be perpendicular to both of them. B of t is always a unit vector. Maybe pause me for a minute, ponder that, and see if you can figure out why that would be the case. And then unpause me and I'll show you. Okay, why is that the case? Let's go back to our friend, the magnitude of the cross product. We learned a while back that the magnitude of A cross B is magnitude A, magnitude B, product, times the sine of the angle between the vectors. So let's apply that to t and n here. Magnitude t cross n would be magnitude t times magnitude n times the sine of the angle between those vectors, theta. And now let's pause and think. It's the unit tangent vector and the unit normal vector. So both of these have length 1. The unit tangent has a magnitude of 1. The unit normal has a magnitude of 1. In terms of the angle, we said that the unit tangent and the unit normal always have to form a right angle. They are always orthogonal to each other. So what that tells me is that the angle between them must be 90 degrees. So I'd be taking the sine of 90, which is 1. So altogether, I get 1 times 1 times 1, which is 1. So what we just figured out is that the cross product has a magnitude of 1. By definition, any vector with a magnitude of 1 must be a unit vector. So B is a unit vector. Kind of a small little side proof. So hopefully that convinces you. Okay, another way, this will be a formula that might be a little bit easier to use depending on the problem. This is another one I would know for B. Magnitude of, not magnitude, the binormal vector can be calculated using r prime cross r double prime. And since we want it to be a unit vector, we would divide by that magnitude, r prime cross r double prime's magnitude. It just prevents you from having to calculate the unit tangent and the unit normal. So it's another one you could use. Fair game for WebAssign if you want to use it, or on a quiz or a test. Okay, so why do we care about all three of these? These three together, the unit tangent, the unit normal, and the binormal vector, as they move along the curve, they form a set of orthogonal vectors. We've already said that all three of them are going to form right angles with each other. And we call this set of T, N, and B, the unit tangent, the unit normal, and the binormal. This is what's called the TNB frame. Sometimes you might hear it called I believe it's pronounced the Frenet frame, based on two mathematicians that spent some time researching this. When I refer to it, I'm going to call it the TNB frame. But again, oftentimes you might hear it called the Frenet frame or the Frenet frame. And it's a framework that basically shows you how the vectors move along the curve as t varies. So this shows up a lot in different branches of math. Differential geometry is a very popular research-based field in mathematics where this comes up. And lots of times you'll see this in applications of spacecrafts. Pilots need to know the TNB frame to be able to calculate things like torsion, how much a plane might be spinning through the air, wing motion, things like that. The TNB frame can help you. So a couple visuals just to show you in pictures. Here's a space curve that I have outlined in yellow, and it shows us the direction that it's increasing is upward and to the right. Focus on a very specific point on that graph, which I'm outlining right now in blue. Couple of vectors we care about in terms of the TNB frame. I'll do them in different colors here. So in red, we've got the unit tangent vector, which points in the direction of the curve. Looks like the curve's moving that way. In blue, we've got the unit normal vector, which tells us the direction in which the curve is turning. Looks like it's turning inward at that point, since the concavity looks like it's concave up. And perpendicular to both of those will be my green vector, which is B. That's the binormal vector. That's orthogonal to the blue one and the red one. And so kind of pretend that was moving along the curve at different points. At one specific value of t, I'll call this T1. There's your TNB frame. As the curve continues to move and get to point T2, now you have a new TNB frame. It really helps to see these in motion, so I'm going to pull up an animation, and I will try to share this with you. It's in your ebook, but I'm going to try and post the link and see if you guys can just click it directly and access this. This is pretty cool. So there's different space curves that I'm going to animate. I'm going to start with the helix, just because that's the one that we've spent a lot of time graphing and doing calculations with. On this graph, what you'll see is the unit normal vector is going to be the one in orange. The binormal vector is the one in blue. And the unit tangent is the one in purple. I'm also going to add the position vector, which comes out of the origin and is going to trace out the helix. And I'm going to animate it. I want you to watch the TNB frame. And it's going to show you really how the TNB frame is what allows you to create this helix. This is what determines the shape of the helix. So if I animate it, you can watch it in real time. As t varies, my values of t are changing. You can see this almost tripod-like shape, and it's showing you the positions of the unit tangent, the unit normal, and the binormal, as well as the position vector as it traces out the helix. And then it starts over. And that orthogonality is preserved no matter what point you're at. Let's go to a different curve. Let's look at, I'm going to click something a little more fun. This one's kind of cool. This one's t cosine t, t sine t, and cosine 2t minus sine t. So lots of trig going on. If I animate it, you can watch what happens as you move along the curve for different values of t. We would expect more rapid change to happen probably about now. Watch how it's going to kind of rotate. Big curvature means more rotation for that TNB frame. It's almost like you're on a roller coaster. Put your arms up. Here comes the little bunny hill. Woo! Who knew math could be so much fun? You guys think about this when you're on the American Eagle? Next time. So anyway, you get the idea. There's a couple more curves you could try it for if I post it. There's that one. This one kind of looks like an egg. I feel like we've used the egg analogy before. It's kind of fun to play with. And you can say, oh, that one had a real fast turning point. There's a lot of curvature going on there, right? Smaller circle means more curvature. So you're going to see a lot more motion on that TNB frame as you hit that little rounded oval. Now, rotate, reverse, reverse to the left. Okay, I'm done. A couple other applications. When would you use this? I mentioned spacecraft motion, being able to calculate curvature, torsion of a shuttle. Race car drivers would want to use it every time they're going to come and bend around a path. Having some knowledge of the TNB frame might tell them how fast to approach that curve, when to hit their brakes, how much twisting and turning they're going to endure during that race so that their car doesn't spiral out of control. Hang gliders, knowing the magnitude of your turns and the twisting motions when you're hang gliding. You can use the TNB frame to calculate motion at different points of your flight. So there's a lot of different applications. Railroad tracks, whenever trains are going to be turning, they have to use the TNB frame to design railways in a successful way so that the train does not derail and go off the tracks when it hits a very steep curvature. So lots of applications you might not have thought about. Okay. So that's what it is. Moving on. Let's end with an example of how to calculate it, and then you're going to do a group or partner practice problem tomorrow during class to give yourself a chance to let some of these calculations sink in a little bit more, but I'm going to show you one of them. In this problem, we are given a helix, 3 sine t, 3 cosine t, 4t. So it looks like it's going to spiral in the z direction since that's the linear factor. And it looks like the radius of the helix, every single trace that I take in the xy plane is going to have a radius of 3, circle with a radius of 3. So I want to calculate the unit tangent, t of t, the unit normal, n of t, and the binormal vector b of t for any general value of t. Sometimes you might have to calculate it at a specific value of t. This is just giving us a general formula for capital T, capital N, and capital B. So let's start with the unit tangent. To get the unit tangent, helps to kind of put my goal. That'll tell me what pieces I need. This would be r prime of t over the magnitude of r prime of t. So I'm going to need r prime. So let's start with that. Off to the side, do some scratch work. R prime would be taking the derivatives of my three components. The derivative of 3 sine would be 3 cosine t. The derivative of 3 cosine would be negative 3 sine t. And the derivative of 4t would be 4. I also need to divide by the magnitude of that vector. So the magnitude, I'm going to square the components and add them together and take the square root. So I would get 9 cosine squared t plus 9 sine squared t plus 16. This should make you think it's looking a lot like sine squared plus cosine squared, which we know is 1. So being a little bit more formal with it, after you see this calculation once or twice, you might be able to just kind of jump to the result here, but I'm going to factor out the 9 so that you can actually see, oh, that's just 1. So this turns into the square root of 9 plus 16, which is square root of 25, which is 5. So that's going to be my denominator. So therefore, t of t, the unit tangent vector, is going to be given by, this was my numerator, and I am going to be dividing by 5. So this is going to turn into 3/5 cosine t, negative 3/5 sine t, and then my last component is 4 divided by 5 would be 4 over 5. And so there is my, and the magnitude of that vector, we know it should be 1. If you want to confirm that, you can check to make sure that that magnitude is 1. Okay, so there's 1/3 of the problem. Unit tangent vector tells me the direction that the curve is moving, not the direction it's turning, which is why we need friend number 2. Come on down, unit normal vector. This will tell us the direction that this helix is turning. This is going to be t prime of t over the magnitude of t prime of t. We found t, we didn't find t prime, so we're going to have to calculate t prime. So let's do that. Calculations off to the side here. T prime, if you look at your unit tangent we just found, is going to be, let's see, derivative of 3/5 cosine would be negative 3/5 sine t. Derivative of negative 3/5 sine t would be negative 3/5 cosine t. Derivative of 4/5 would be a nice 0. So it looks like we're actually projecting now into the xy plane. We need the magnitude to make it a unit vector. So the derivative has a magnitude. Let's see. Squaring and adding components and square rooting, we're going to get 9/25 sine squared t plus 9/25 sine squared t plus 0. Same trick. Oops, sorry, cosine. Cosine squared t. Factoring out the 9/25 sine squared plus cosine squared would leave us with 1. So this is going to be just the square root of 9/25, which would be 3/5. So to calculate this now, n of t, I'm going to take my t prime and I'm going to divide out 3/5 from each of those components. So negative 3/5 divided by 3/5 would be negative 1. So this will be negative sine t. Negative 3/5 cosine divided by 3/5 would be negative cosine t. And then last but not least, 0 divided by 3/5 is going to stay 0. Okay, so it looks like the unit normal vector is actually absent of any z components. It looks like it's completely determined by the x component and the y component of that vector. So it looks like a circular projection in the xy plane. Okay, so we've got 2 of them now. To complete the TNB frame, we need a vector orthogonal to both of those, and those 3 vectors will then uniquely determine that space curve. We need B. We saw a couple ways you could calculate B. I gave you a formula on the last slide in terms of R prime and R double prime. Considering we've already calculated T and N, it doesn't look like the results are too awful. I think it would be safe to just calculate T of T cross N of T, but you could use the other one that I gave you also in terms of R. Remember, T comes first, N comes second. We learned about T first, it's got to come first. We learned about N second, it's got to come second. So you are going to have to take a determinant. Not too painful, hopefully. IJK, put your unit tangent vector in the middle row, 3/5 cosine T, negative 3/5 sine T, and 4/5. Put your unit normal vector in the bottom row, negative sine T, negative cosine T, 0. And for the probably 30th time this year, cross products, woo! Cross off first row, first column, we're going to get 0 minus negative, so plus 4/5 cosine T, minus J, cross off first row, second column, we're going to get 0 times 3/5 cosine T, so 0, minus negative, plus 4/5 times sine T, plus K, remember your vectors, cross off first row, third column, we're going to get the one that has the most to it. Negative 3/5 cosine squared T, minus, so let's keep track of that. Minus is going to be minus. Odd number of negative signs. So this is why it's so important you write things out. If you try to do these things in your head, I know on some of the original quizzes, some people were doing cross products in their head. With numbers, that's not probably going to lead to too many algebraic errors. When you start doing it with lots of variables and sines and cosines and negative signs, the more you do in your head, the more that's going to go in a bad direction. So my advice is, even though it's tedious, I would highly suggest you write steps out. That also allows you to get partial credit on a quiz or a test. Okay. Minus 3/5 sine squared T. Okay, so let's see what we get. This part right here, I'm going to clean up just a little bit. This looks a lot like I could factor out a negative 3/5, and then I get my favorite cosine squared T plus sine squared T, which is 1. So this last component really just turns into negative 3/5. So, summarizing, B of T, first component, 0 plus 4/5 cosine would be 4/5 cosine T. Second component, minus 4/5 sine T. And last but not least, we're back to having a Z component. It disappeared for the normal vector, but for the binormal vector, we actually get a constant Z value of negative 3/5. And again, you could plug in, if I asked you now at any value on the curve, when T is equal to pi, what's the binormal vector? If T is equal to pi over 2, what's the normal vector? You could just simply plug in the values. Another nice thing you can do, I want to mention, this will help you tomorrow on the problem you do. Let's say you already calculated T and you already calculated N, and you wanted to find something like the binormal vector at the point pi. You don't actually have to go through the calculation with all the T's. You could calculate, you already found the formula for T. You could do T of pi cross N of pi with the numbers themselves. You don't actually have to do it in terms of T. So that's a benefit, is if you're not asked to find the general formula for the binormal vector, if you're only asked to find it at a specific point, do the hard work for T and N, but then you can just plug in the points and your determinant gets filled with numbers instead of getting filled with T's. So that'll help you tomorrow, because you're going to have to find the unit tangent, unit normal, and you're actually going to have to find the binormal vector at a specific point on the curve. You're going to talk tomorrow as a group about what T value that's going to be for. But use that advice to save yourself some algebra. Okay, that's a lot. Hopefully, pause, go back, watch some parts again if you need to pause some of the algebra and watch it again, especially the conceptual side of this. I know this is a little bit different than what you've done in the past, but I think it's worth it, especially when you get to see cool pictures like that. Okay, so this is some really cool math, and we saw it has a lot of cool applications, and we're going to kind of dive even deeper next week. So make sure that you practice this part, do your homeworks on WebAssign, do your packet, talk about the problem tomorrow as a group. I will have a key up to this problem that you're going to do in the chapter 13 Google Docs so that you can be checking one step at a time along the way to make sure you're on the right track. These calculations tend to build off each other, so you want to make sure you check them one at a time before you check all of them at the end. All right, happy mathing. TNB, I'm just going to end with this. TNB is the new LOL. Text it to your friends. See if they even know what you're talking about. Okay. See you.